The next thing we're going to discuss is how to calculate binomial distributions on the calculator. So when we were discussing the normal distribution, we used normal CDF, but there is also a distribution in the calculator that allows us to do binomial distributions. And one of them is with PDF and the other one is with CDF. And they are different calculator functions. They do calculate different things. So PDF is our probability distribution function, and it is used in a distribution when you're trying to calculate when the probability of x equals a specific value k. So when we're doing probability x equals k, we use the binom PDF function, and we need n, p, and k. So remember, n is our sample size, p is our probability of success, and k is whatever value we're trying to find. So using the same examples from above, the probability that Calvin gets exactly 3 correct, in order to get to binomial PDF, I hit second vars, and then I'm going to scroll all the way down to the letter A, and it's going to say binom PDF. So once I select it, depending on the calculator you have, it might go directly to the screen where it says binom PDF parenthesis, or it'll take you to a screen where it asks you for your trials, your probability, and your x value. It's in the same order no matter what. So the first number you plug in is n, your sample size. And because we're talking about 5 questions, n is 5. The next thing you plug in is your probability, which in this case is 0.5, my probability of success. And because I'm looking for exactly 3 correct, my next value is going to be 3. And then we're going to hit enter, and we're going to get 0.3125, which is the exact same thing we got when we used the formula for binomial distributions, and then again when we were just using regular probability distribution. The next calculator feature is CDF, and it stands for cumulative distribution function, and it's used when you're trying to calculate with an inequality. Now, unlike what we did on our previous example when we were doing greater than or equal to, in the calculator, CDF for the binomial distribution can only calculate the probability of x being less than or equal to some value k. So it's not always just plug it into the calculator and hit enter like with binomial PDF. You have to pay attention to whether or not the problem itself is a less than or equal to, greater than or equal to, because that changes how you plug it into the calculator or how you calculate the final answer. So when we were looking at the probability Calvin will pass, we were specifically looking at the probability x is greater than or equal to 3. So if I want to get to binom CDF, I still go to second vars. Now, depending on your calculator, you're either going to scroll down to the letter B or the letter C. It depends on the calculator. So whichever your calculator is, please write that letter. Like if you scroll down to B and it says binom CDF, write B. If you have to scroll down to C to see binom CDF, please put C. So whichever one applies to your calculator. So our problem says the probability x is greater than or equal to 3. So I can't just plug that in for the binom CDF because it's not a less than or equal to. So the probability that he passes is the same thing as 1 minus the probability he fails, because the probability he passes plus the probability he fails have to equal the 100%. So I'm going to do 1 minus, and then the probability he fails is the probability he gets less than or equal to 2 problems correct. So in my calculator, I'm going to do 1 minus, then I'm going to do second vars, and I'm going to go to binom CDF. I'm going to plug in n, still 5. My probability of success is still 0.5. And then I'm going to plug in 2 for k. And when I hit enter, I get 0.5, which is what we got when we did it above. Okay. The last thing, and it's very, very important thing when we're talking about binomial distributions, is that a binomial distribution is a discrete variable, which means the inequalities for a cumulative distribution function, an equal to does matter. And if you have an equal to or strictly greater than, it does change how you plug it into the calculator based on that. So you want to make sure you're paying attention to your inequality when you're doing a cumulative problem and whether or not it's greater than, less than, greater than or equal to, or less than or equal to. So the next thing we have here is 4 examples. And what I want you to do is try each example on your own first using either the binom CDF feature on your calculator or the summation feature on your calculator, whichever one you're most comfortable with for the inequalities. And then after you try it on your own, then press play to see how you're supposed to plug it in. So the example says x is approximately binomial with n equals 5 and probability success of 0.4. So I went ahead and I wrote that up. N equals 5 and p equals 0.4. So the first problem is the probability x is less than or equal to 1. If I want to use binom CDF, I want to use my calculator, I don't have to change anything because it's already of the form probability x less than or equal to k, which is exactly what binom CDF does. So I'm going to go to binom CDF. My trials, or my n, is 5. My probability of success is 0.4. And k is the number after my inequality, which is 1. And then I hit enter. And I'll go over the correct answer here in a bit because I'm also going to talk about summation. Your other option is to do the summation feature on your calculator. So when I do the summation, I'm going to start, in this case, if I'm looking at everything less than or equal to 1, there's only one number less than 1. So I'm going to start at 0 and I'm going to go to 1. And I'm going to have 5ck because my sample size, I'm doing 5 trials, times my p, which is 0.4, to the k, times, now my probability of failure is 1 minus the 0.4, so it's 0.6 to the 5 minus k. And then I'm going to hit enter. In both cases, you end up with the decimal 0.337. So both, no matter which way you chose how to do it, you should end up with 0.337 either way. Next, we're going to look at the probability x is less than 3. Now, I can't go straight to using binom CDF because it's not of the less than or equal to. So if I'm looking at anything less than 3, that's the same thing as saying that I'm looking at everything less than or equal to 2. Because everything less than 3 is 0, 1, and 2, and everything less than or equal to 2 is 0, 1, and 2. So if I'm going to use binom CDF, I'm going to have 5, 0.4, 2. If I'm going to do the summation, I'm going to start at 0, and I'm going to go to 2. I'm going to have 5ck times 0.4 to the k times 0.6 to the 5 minus k. So the only thing that's going to change for the summation one on each of these is what you start with and what you end with depending on what your inequality is. The equation that you plug in is the same every time. And in both cases, you end up with the decimal 0.683. So those are just examples of a less than and a less than or equal to. We're also going to take a look at examples of greater than or equal to and greater than. So the next one we have the probability that x is greater than or equal to 4. So I have to change this to a 1 minus situation. So everything greater than or equal to 4 is 4 and 5 because my sample size is only 5. So I'm going to do 1 minus the rest of it, which is the probability x is less than or equal to 3. So for the binom CDF, it's 1 minus binom CDF, and then we'll have 5, 0.4, 3. If I choose to do the summation, I'm going to do 4 to 5. And then we'll have 5ck times 0.4 to the k times 0.6 to the 5 minus k. And again, both of these are going to result in the same answer of 0.087. The last one we have here is, there's 2 different ways you can look at it. So the first, if I'm looking at the probability x is greater than 4, because my sample size is only 5, the only thing greater than 4 is 5. So the easiest way to probably look at it is to look at it in a binomial PDF situation, because the only thing greater than 4 is 5. So if I do binom PDF, I have 5, 0.4, 5. Okay. The other option is to look at it as a CDF situation. So I change it to 1 minus the probability is x is less than or equal to 4. So if you have a strictly greater than inequality and you switch it to a situation where you can use binom CDF, the number doesn't change because now you want to include it when you do the less than or equal to. So then I can look at binom CDF for 5, 0.4, 4. Okay. Both of these result in the same answer of 0.0102. If you wanted to do the summation here, it's the most difficult one to do here because you'd have to do a 1 minus situation with the summation and do 0 to 4, which is a lot more work. So really your 2 best choices here are to think of it as a binom PDF situation or the binom CDF. Next thing we're going to look at is how to calculate mean and standard deviation for binomial random variable. So it has its own mean and standard deviation formulas, and they're actually the most simplest of mean and standard deviation formulas. So if you have some binomial distribution with sample size n and probability of success p, the mean is just n times p, and the standard deviation is the square root of n times p times 1 minus p. Another way to think about it, we're going to add another variable. So we're going to let q equal your probability of failure. So another way to think of the standard deviation is the square root of n times p times q. So you do the probability of success times the probability of failure times your sample size, then you take the square root. So going back to the example with Calvin's quiz, we want to find our expected value, which is the same thing as mean. So remember, mean is also expected value, E of x, and his standard deviation. And then we want to interpret those in context. So let's start with his mean or his expected value. So E of x is going to be n, which is 5, times 0.5, which is 2.5. Our standard deviation x is going to be the square root of 5 times 0.5 times 0.5. which is going to give us 1.12. So when it comes to interpreting, we can say if Calvin took many quizzes, we would expect him to get 2.5 correct. Now you can't really get 2.5 questions correct, but we are going to keep it as a decimal. Okay. Next is our standard deviation, which is the variation from our mean. So the typical deviation, because it's standard deviation, from the expected value is 1.12 questions correct. So we expect him on average to get 2.5 of them correct, but he can deviate by that by 1.12 questions in either direction. Again, we're going to end up with decimals from the mean and standard deviation a lot of the time here, and it's not always going to make sense for our situation, but we are going to leave them as decimals so that we're being accurate in our interpretation. Okay. Our next example says that suppose the probability that any random freshman girl will agree to go with Nick to the senior prom is 0.1. Suppose Nick asks 20 random freshman girls to the prom. What is the probability that exactly one will say yes, that at least one will say yes, and then on average, how many freshman girls will agree to go with Nick to the prom? And what is the standard deviation of this binomial distribution? All right, so first thing we're going to do is define our variable x. So x is the number of girls who say yes to Nick. Our n is 20, and our probability of success is 0.1. So the first part is the probability that exactly one will say yes. So that's the probability x equals 1. So depending on how you want to do this in your calculator using either the exact formula or binom PDF, both work. I'm going to do the work for the binom PDF. So binom PDF, our trials is 20, probability of success is 0.1, and then our k is 1. Plugging that into the calculator, we hit enter, and we are going to get 0.27. The next one is the probability that at least one will say yes. So that's the probability x is greater than or equal to 1. So again, we want to change this to a situation where I can either use CDF or PDF depending on how it changes. So this is going to be a 1 minus. Now, if I wanted to switch it to a less than or equal to, it'd be the probability that x is less than or equal to 0. But since 0 is the smallest thing I can get, it's the 1 minus the probability that x equals 0. So it's 1 minus the probability that no one says no. No one says yes. Sorry. 1 minus the probability no one says yes, which is going to be 1 minus binom PDF 20, 0.1, 1. Sorry, 0. And once we hit enter, we'll get 0.878. So he has a fairly good chance that if he asks 20 girls, at least one of them will say yes to him. All right, so next is our expected value. So if Nick were to ask groups of 20 girls multiple times, on average, how many would he expect to say yes? So that's 20 times 0.10, which is going to be 2. So on average, Nick can expect 2 girls to say yes to him. Our standard deviation is going to be the square root of 20 times 0.1 times 0.9, which is going to be 1.34. So that means that the typical deviation from the expected number of yeses is 1.34, which is not great considering his average is only 2. The last thing we are going to discuss is the geometric distribution. So for a binomial random variable, x equaled the number of successes in a fixed number of trials. When we look at a geometric random variable, we use the variable y, and it's the number of trials until you get the first success. So we're basically saying, let's solve for n in this situation. So for example, I want to know the number of trials I have to do in flipping a coin until you get heads, rolling a die until you get a 6, throwing darts at a dartboard until you hit the bullseye. So that's what a geometric random variable will do. It finds the probability that you get your first success on a specific trial. So a geometric distribution has properties as well, and there's only one difference between the conditions for a binomial and a geometric distribution. So instead of we had bins for binomial, we have bits for geometric. So the first condition is the same. It has to be binary. So you have to have 2 possible outcomes, success or failure, just like before. We also have to have independence. So your trials have to be independent. The next variable is where we're doing. So n was our number of observations. Now we have t, which is our trials until first success. And then lastly, S, our same probability of success. So your probability of success, P, doesn't change from trial to trial. So only one difference in the conditions. So let's talk about how the geometric probability formula works. So for example, you're going to roll a 6-sided die, and y is going to equal the number of trials until you roll a 6. So we're going to go through this kind of where you discover the formula and you can see where it comes from. So what's the probability that you roll a 6 on the first trial? Well, considering in a die there is only one outcome that's a 6, I have a 1 in 6 chance of it happening on the first roll. Okay. Now let's take a look at the probability that you roll another number on the first trial, but a 6 on the second trial. So the first trial is every number but a 6, of which there are 5. The second trial, it is a 6, and there's 1. So we have 5/6 times 1/6, which is going to give us 5/36. Then what's the probability that you roll another number on the first 2 trials, but a 6 on the third trial? So my first roll is 5/6. My second roll is also 5/6. I could technically roll the same number twice on the first 2 trials as long as neither of them are a 6. So I could do a 1 and a 1, a 2 and a 2, or they could be different. And then my third roll is the 1/6, which gives me 5 times 5 is 25 over 6 times 6 times 6, which is 216. So let's go ahead and look at this in a distribution. So this time my variable is y, and then the probability of y. So with a geometric probability distribution, the smallest number it starts with is 1. You can't start on 0 because we're looking for our first success. So it could happen on the first, the second, the third, the fourth, and then we can actually keep going. All right, so we have 1/6, then we have 5/36, then we have 25/216. And you kind of get the idea that my numerator keeps getting multiplied by 5 and my denominator keeps being multiplied by 6. So it's going to be 125 over 1,296. And I can keep going. So unlike the binomial distribution where there were always a set number of trials, set number of outcomes, the geometric probability distribution could go on forever. There is no end, which is why we don't use probability distributions, because they can go on forever. So can y be 0? We've already talked about this. No. Because we're looking for our first success, the smallest number I can have is 1. When do we stop the table? Never. Because you could technically go on forever without a success. You're not guaranteed to have a success. And then what pattern are we noticing? So if we're looking at it, so our formula, we had 1 minus the probability of success, and then raised to our number of failures, which in this example kept changing, times, and then there's only one probability of success. So if I had 2 failures first, I did 5/6 times 5/6. If I'd had 3 or 4, but there's only ever one success. So unlike the geometric distribution where we could have multiple successes and no failures, or multiples of both, or no success and all failures, or whatever, for geometric, there's always one success and then the rest are all failures, depending on when you are looking for that one success to occur. So we can write this as a formula similar to when we did the binomial distribution. So y has a geometric distribution with a probability of success p on each trial. K represents the trial that you get your first success. So our formula, the probability y equals k, is 1 minus p to the k minus 1 times p. So the reason why we have k minus 1 for that exponent is that the number of failures is all of the trials leading up to that trial that the success happens on. So using our dice example, what's the probability it takes you 5 rolls until you get a success? So that's the probability that y equals 5. So we already know that the probability of failure is 5/6. So our first 4 rolls were failures times our last roll that was a success. And we get 0.0804. What's the probability that it takes you 10 rolls until you get a success? So that's the probability y equals 10. So that means we had 9 rolls of 5 out of 6 times our 1 success 1/6, which is 0.0323. Kind of see that as K increases, our probability is going to decrease because it gets less and less likely that it's going to take you that many trials until your first success. Now let's take a look at an inequality situation. So what's the probability that the 6 happens within 3 rolls? So that's the probability that y is less than or equal to 3. So that's the probability it can happen on your first roll, your second roll, or your third roll. All right. I could do a summation here, but this isn't that difficult of a formula. I don't have to do an NCK. So I'm not going to show you how to do a summation here. I'm just going to go ahead and use the formula. So we know the first success is 1/6. We know the second success is 5/6 times 1/6. And then we know the third is 5/6 squared times 1/6, which ends up being 0.421. The last example we're going to look at is the probability that it takes at least 4 rolls to get a 6. So that's the probability that y is greater than or equal to 4. Now, with the geometric distribution, we could leave it as a greater than or equal to because we had a set number of trials. But with a geometric distribution, I could technically go on forever. There is no sample size. So if I have an at least situation where I have a greater than or equal to inequality for my probability, I have to change it to a less than or equal to problem. So I have to change it to 1 minus the probability that it takes less than 4 rolls. I have to. I don't have a choice because there's no ending point for greater than or equal to. And we already found that probability, so it's going to be 1 minus 0.421, which is going to be 0.579. So at the bottom here are where you can find the GeoMet PDF and the GeoMet CDF on your calculator. Again, to get to this feature, you'll do second vars. Now, if it's not E or F on your calculator, if it's something else, please change the letters to match your calculator. But just like with the binomial distribution, GeoMet PDF will only do when the probability of y equaling a specific value k, and GeoMet CDF only does the probability of y less than or equal to some value k, just like with the binomial. Next, we have the mean and standard deviation of our geometric random variable. So the formula for the mean, or the expected value, is going to be 1 divided by p. And it tells us how many trials we expect to run before we get our first success. And then the standard deviation is the square root of 1 minus p all over p. Again, if I let q be the failure, I can also think of it as the square root of q over p. So that's the typical number of trials that deviate from the mean. Also, a lot easier formulas than typical mean and standard deviation. So we have an example that says to start her old lawnmower, Iris has to pull a cord and hope for some luck. On any particular pull, the mower has a 20% chance of starting. So we want to find the probability that it takes her exactly 3 pulls to start the mower. So that's the probability that y equals 3. I don't often use binomial PDF or binomial CDF, mainly because this formula, again, very easy. So if the probability of success, P, is 0.20. That means 1 minus P is going to be 0.80. So our first two trials are failures, so 0.80 squared times 0.20, which is 0.128. Okay. B, we want the probability that it takes more than 10 pulls to start the mower. So that's strictly greater than 10, which means I need to do 1 minus the probability that it takes less than or equal to 10. Sorry, less than or equal to 9. So here I'm definitely going to use the binom CDF, mainly because n is so large. Like if I were looking at least 2, I would probably just use the formula. So, sorry, not binom, geo. So with the GeoMet CDF, I only have 2 values. I have my probability and I have my x value. So my probability is 0.20, and in this case, my x value is 9, and we get 0.134. Okay. And lastly, how many pulls do you expect it will take Iris to make? So that's our expected value of y, which is going to be 1 over 0.20, or 0.2, which is going to be 5. So we expect that it will take Iris 5 tries before the lawnmower will start. If you have any questions over the binomial distribution or the geometric distribution, or how to use the calculator at any point, please let me know.